Before we start looking at some specific functions, I'd like you to think about what a graph really is representing. A graph is just a picture of all the ordered pairs which make an equation a true statement. So if we're looking at a linear function, and we know the equation of that function, then we've got a description of all of the x and y values which can be paired and then substituted in the equation to make a true statement. Now there's more than one way we can express the equation of a linear function. One way is slope-intercept form, and the slope-intercept form for this line that we see in the graph is y equals 2x minus 3. We can also write the equation of a line in point-slope form. For this line, one version of point-slope form would be this: y plus 5 equals 2 times the quantity x plus 1. That equation would look a little bit different if we chose a different point to use in our equation. And we can also write the equation of a line in standard form. For this line, standard form would be 2x minus y equals 3. Now getting back to this idea that a graph is just a picture of all the ordered pairs which make an equation a true statement, let's pick out a point on this line, like 4, 5, and show that it really does make all of these equations true. In slope-intercept form, we have the true statement 5 equals 5. In standard form, we have the true statement 3 equals 3. And in point-slope form, we have a true statement 10 equals 10. No matter what point we choose that's on this line, it will make all of these equations, which are all equations for this same line, a true statement. So if we choose the point 2, 1, and substitute 2 for x and 1 for y in all of these equations, we get true statements for all equations. So that's one way you could always check to see if a line that you've drawn really is a line that's being described by the equation that you've written. You could check a couple of points that are on the line and see if they make that equation a true statement. Now let's talk a little more about slope. Slope is a measure of the steepness of a line. It's also a ratio of the vertical change and the horizontal change that we see when we look at any 2 points that are on the line. And it describes a rate of change. The line that we see here would have a positive slope. The number that represents the slope would be a positive number. This line would have a number for slope that would be negative, so it has a negative slope. This line has a slope that's equal to 0, and this line has an undefined slope. Now you may remember slope as rise over run, and that's certainly a good way to remember how to find the slope of a line. We might also want to think about slope as being a vertical change divided by a horizontal change. And if we write that in mathematical notation, we could write that as a delta y over delta x. That's the change in y divided by the change in x. Now you also might remember that to find the slope of a line, we can pick 2 points that are on the line and find the difference of the y-coordinates of those points and divide that by the difference of the x-coordinates. That's actually a very, very important quotient that we have. It's called the difference quotient, and we're going to see that a lot as we work through our problems in calculus as well. So let's take a look at 2 points that are on this line. For example, -3, -2, and 3, 4. If we use those 2 points to find the slope of the line, we would find the difference of the y-coordinates and the difference of the x-coordinates, and then we would make a quotient out of those, and we'd end up with 6 over 6. If you look at the graph, you can actually see those changes. The change in y is 6, and the change in x is 6. So that's why we've got 6 over 6 for our slope. Now obviously 6 over 6 simplifies to 1. Now let's go back to that slope-intercept form for the equation of a line. In general, slope-intercept form is written y equals mx plus b, where m, the number that multiplies the x, is the slope, and b is the y-intercept. So if we have an equation in this form, we can very easily find the slope and the y-intercept of the line. Or if we have the graph of a line, we should be able to write the equation fairly easily if we can find the slope of the line and the y-intercept of the line from the graph. Now for this line, we can see that the slope is 2 over 1, or just 2, and the y-intercept is negative 3. So the equation of this line in slope-intercept form is y equals 2x minus 3. What if we want to graph a line? Can we use this slope-intercept form to do that? Well, we can if the equation is in slope-intercept form. This equation isn't. It's in standard form. But if we solve the equation for y, then we can identify the slope and the y-intercept. In this case, the slope is negative 3/4, and the y-intercept is 2. So to graph the line using this information, the first thing we'll do is graph the y-intercept. And then, since the slope is negative 3/4, we can go down 3 and to the right 4 to find a second point on the line. If we connect that second point to our y-intercept, we'll have the line graphed. What if we want to write the equation of a line with a slope of 4 and a y-intercept of 7? Well, this is pretty easy because we know the slope and we know the y-intercept of the line. So we have all the information we need to write the equation of this line in slope-intercept form. Y equals 4x plus 7. What if we want to write the equation of a line with a slope of 4 which contains the point 1, 3? Well, now we have a little more work to do. We know what the slope of the line is, but we don't know the y-intercept. There's a couple of ways we can handle this. One way would be to say, well, we know what this slope-intercept form looks like, and it's really telling us a relationship between a point, the slope of the line, and the y-intercept of the line. So let's use the information that we have. We know that the slope is 4, so we'll substitute 4 in for m. We know that a point on the line is 1, 3, so we can substitute 1 for x and 3 for y. And then the only thing we don't know is b, which is our y-intercept. So if we solve the equation for b, we'll find out that our y-intercept is negative 1. And that's all the information that we need to write the equation, since we already know what the slope is. So y equals 4x minus 1. Now there's actually another way to do this same problem, and that's by using point-slope form. Point-slope form looks like this: y minus y sub 1 equals m times x minus x sub 1. The m is still slope, and the x sub 1 and y sub 1 are the x and y coordinates of a point on the line. So since we know the slope and we know a point on the line, we could just use point-slope form to write the equation. We'll substitute 4 for m, 1 for x sub 1, and 3 for y sub 1. Now if you look at that, and you look at the equation that we got in the first case, y equals 4x minus 1, those two equations look completely different. But we started off with the same information. They both represent equations of the same line. And in fact, if you simplify the equation that we have in point-slope form and write it in slope-intercept form, you'll see that we do have exactly the same equation. Now there's two special cases for lines, and those are equations that have only one variable in them, either just the x or just the y. Let's take a look at x equals 4. X equals 4 is a graph that has ordered pairs with x coordinates that are all 4. So that would be a vertical line. Every point on this line has an x coordinate of 4, but we have lots of different y coordinates along that line. For y equals -3, we would have a graph that has all ordered pairs with y coordinates of -3. So that would be a horizontal line. So let's move on to quadratic functions. Now we're going to have lots of different techniques for graphing functions as we start to look at calculus. But for now, let's just think about the general shape of a quadratic function and some of the information that we can get out of the equation of a quadratic function. So the graph of a quadratic function, f of x equals ax squared plus bx plus c, is also called a parabola. It will always be a cup-shaped curve. It will open upward if a, that's the coefficient of the x squared term, is positive, and it will open downward if a is negative. It has a turning point, which we're going to call a vertex, at a point that has coordinates negative b over 2a, f of negative b over 2a. And the vertical line x equals negative b over 2a will be the line of symmetry for the parabola. So when we graph parabolas, we're going to make sure that we can find that vertex because it's going to tell us something about the line of symmetry, and that will make it easier to graph the parabola. So suppose we want to graph f of x equals x squared plus 2x minus 3. Well, the first thing we could do is try to find that line of symmetry. And the equation of the line of symmetry is x equals negative b over 2a, which in this case is negative 2 over 2 times 1, or negative 1. So x equals negative 1, that's a vertical line, is our line of symmetry. The vertex is on that line of symmetry, so the vertex has an x coordinate of negative 1. To find the y coordinate to go along with that x coordinate, we'll go back to our idea of input-output. We'll use negative 1 as our input into our f function, which leads us to an output of negative 4. So our vertex is at negative 1, negative 4. Now to find more points on the graph, we can remember that the vertex is going to be the lowest point on this graph. We know it's lowest because the value of a in this equation is 1. That's from 1x squared, which means the parabola opens up. So the vertex is going to be the low point on our graph. We also know that if we find points on either side of that vertex, we'll see some symmetry. So for example, if we let x be 0, y would be negative 3. And if we let x be negative 2, y would be negative 3. So do you see the symmetry going on? How about if we let x be 1? Substitute 1 in for x in our equation, and y is 0. If we let x be negative 3, y is also 0. So if we graph those points, we're going to see symmetry in our graph. You'll also notice that vertical dotted line that goes through negative 1 on the x-axis. That's our line of symmetry, the line x equals negative 1. And we can see that the parabola is symmetric on either side of that line. The line of symmetry isn't part of the graph, but it does help us to graph the parabola. Now another question we might be asked about quadratic functions is to do what's called solving the function. That just means we're looking for all the values of x which will make the function equal to 0. So what we're really solving is this, x squared plus 2x minus 3 equals 0. In this case, we can factor the quadratic expression, set each of the factors equal to 0, and solve to get two solutions, x equals -3 or x equals 1. So what that means is, if we substitute -3 in for x in our equation, we would get 0 back out, or if we substituted 1 in for x, we would also get 0 back out. When we were graphing f of x equals x squared plus 2x minus 3, these values that we just got in solving the equation are actually in the table here and here. When x is -3, y is 0, and when x is 1, y is also 0. And those two ordered pairs show up in these two places on our graph. So solving this quadratic equation by setting it equal to 0 and then finding the values of x that make a true statement is also finding our x-intercepts for the graph. Now sometimes quadratic equations are not factorable, and in that case we can use the quadratic formula to solve the equation. So if we have a quadratic equation in standard form, then we can find the values for x by finding -b plus or minus the square root of b squared minus 4ac all over 2a. So let's say we want to solve this equation, 3x squared minus 4x equals 2. The first thing we would try to do is put it in standard form and factor, but this one won't factor. So we'd want to use the quadratic formula, substituting 3 for a, -4 for b, and -2 for c. Now when we do that, we get an expression that looks like this, and we can do a little bit of simplifying by adding the 16 and the 24, and then if we look at the 40, 40 has a perfect square factor of 4 in it, which means we could simplify that radical expression as 2 times the square root of 10. Now be very, very careful when you're simplifying these expressions, because remember, if you're going to simplify a fraction by canceling, you can only cancel common factors that you see in the numerator and denominator. So we'd want to factor a 2 out of both the numerator and denominator so that we can cancel those common factors and get our final completely simplified result. Now that represents two numbers, 2 plus the square root of 10 over 3, and 2 minus the square root of 10 over 3. If we were actually going to graph a function and use these two values as our x-intercepts, we would probably pull out a calculator and find some sort of decimal approximation for those two numbers. But keep in mind that the radical values that you see, 2 plus or minus the square root of 10 over 3, are the exact solutions for the equation. Now the last thing we want to talk about is exponential expressions. There are lots of exponent rules that you remember using in algebra, and you're going to have to brush up on those rules so that you can use them to simplify expressions. We'll just talk about a couple of them right now, and then you'll get a chance to practice more later on. Let's look at a few expressions and see how we can simplify them. Rewrite the following as an equivalent expression with a rational exponent. That means a fractional exponent. So if we're looking at the fourth root of x, we have to remember that the x that we see underneath the radical is really an x to the first power. So the fourth root of x to the first power is x to the 1/4 power. The cube root of r squared is the same thing as r to the 2/3 power. To simplify using exponent rules, sometimes it's useful to think of these expressions in their radical form while we're simplifying. So for example, 8 to the 5/3 is the same thing as 8 to the 1/3 to the 5th power. 8 to the 1/3 is the cube root of 8, which we know is 2. And 2 to the 5th power is 32. So as usual, you're going to get a chance to practice some of these problems in class and in your homework, and we'll see how much of this algebra comes back to you as you get a chance to practice it.